All right, students. Welcome back from spring break. So we're going to continue today in Chapter 7, and we're going to talk about, just remind you the concept of resolved stress, resolved shear stress. We're going to talk about slip systems, and we're going to talk about how to calculate the resolved shear stress and predict whether something is going to slip. So that's kind of our goals today. So let's review a couple concepts that we left off with. The first one is this concept of resolved shear stress or resolved stress. And you may remember last class we talked about in physics resolving a force into a couple components in different directions that you might be interested in. So if we drew a figure here, let's say we had a cylinder of material and we had a tensile stress in this direction, but we were interested in, well, what's the stress on this plane, and we were interested in resolving that into a shear stress component. So we'll call this tau prime, and a tensile component, sigma prime, that we can do that. So we'll say, remember, one, we can resolve a stress to get tensile and shear components. And then we'll also remind you that it's a shear stress, so it is a shear stress that causes slip. Or we could also say, instead of slip, dislocations move. So it's a shear stress that causes dislocations to move, or planes of atoms to slip past each other. So that was one concept that we talked about before, but I wanted to review. And then let's talk about this concept of slip here again. And remember, we said slip is easiest or preferred on certain planes and in certain directions, okay, and certain directions. You may remember that these are the close-packed planes or planes of highest density, and the close-packed directions, or where the atoms are touching on those planes. So we'll actually specifically talk about what those planes and directions are for different crystal structures that we've talked about here in just a second. And this idea of a slip system, we'll define that. A slip system is a plane and a direction on that plane where slip occurs. So the direction, the key thing in that statement is that the direction has to be on the plane. It can't slip out of the plane. So the direction on that plane where slip occurs. So we started talking about this last time, but we said, okay, for FCC metals, which are the really ductile metals, The types of planes that are close-packed were the 1-1-1 type planes. Now I'll draw specifically the 1-1-1 plane, but we said it's the planes that stack up diagonally, so I'll draw one of those. It's this one, 1-1-1. So 1-1-1 type planes, that's shown right there. And on that plane, 3 directions. And that's where the atoms are touching, you may remember anyway. Those directions that go across the faces like that are the 1-1-0 type directions. So I'm using that notation because I'm not talking about just one direction. I'm talking about these directions that go across the faces. Now you may remember we took this plane out, and drew the atoms. And we said they were touching along this plane. So here are those directions. And also, we could relate this, you could figure out the Burgers vector, which we said is the magnitude and direction for slip, because it has to slip from one equivalent location on one of these directions to another. So I'm going to draw in a real dark line right there. This would be equivalent to the Burgers vector. See, it slips from that position up to this position. So it's kind of half of one of those directions. Now we could draw some of the other ones so that you get an idea. There are other 1-1-1 planes in this family, and each of them have 3 directions. So I'll just draw a couple here. Or maybe I could draw all of them quickly. Here's one. See, it goes across there, and there are 3 directions on there. Draw another cube here. Just try to go through these really quickly just so you see what I mean by there's lots of possibilities here. So another one is this one here. There are 3 directions on that one. And let's see, we already drew, the final one would be, oh, this one right here. Okay, and it's got 3 directions. But you get the idea. And there are 4, so there are 4 1-1-1 type planes, and each one has, we'll say each has 3 1-1-0 directions. So that means there are 12 total systems here. Or another way you could put that is there are lots of possibilities for slip. So depending on how the tensile axis is oriented, there's a good chance that one of these planes and directions is going to be favorably oriented so that slip occurs pretty easily. Now let's take a look at this figure from your book here, but it talks about what we just talked about. There's the 1-1-1 type plane, and there are 3 directions on that plane. We could even name them. Those specific directions on that plane. This one right there is the -1-1-0 plane. This one is the O-1-1. You can see they're all in the 110 family, and then this one right here is the 101 bar direction. And they've shown those directions over there on kind of a top-down view of that plane. Now similarly, we could talk about other crystal structures, the main ones that we've talked about, like BCC. So BCC we think of as being kind of ductile metals, not as ductile as FCC, but let's take a look at those. You may remember at the end of last class period, we said, okay, there are no closed-packed planes in BCC, but there are some that have higher density than others. And the ones that have the highest density are these type of planes that could cut across diagonally. Those are the 110 type planes. And on that, if you were to draw where the atoms touch, they touch along here. So those two directions, they go all the way across, are two slip directions on that plane. So those are the 111, because they go all the way across the body diagonal, type directions. Now again, we could specifically label those. So that plane is actually the 101 plane that I've drawn, but it's in that family. And those directions, this direction right here is the negative 1, 1, 1 direction. And then this one that goes across the other way right here is the negative 1, 1 direction. All right. But you get the idea. And we could also go through all of those possibilities. You actually had a homework problem like this at one point in chapter 3 where I had you draw all of the 110 type planes. So we could do that really quickly. They're all the ones that go cut across like diagonally at a 45-degree angle. So it's this plane and this plane in the left box there. It's this plane and this plane in the box in the center, and then this plane and this plane. And each one of those has two directions, like the example I put up above. So we've got 6 110 planes with two directions on each. So again, we've got 12 total systems here. So we've got quite a few possibilities for slip there. Not quite as easy as FCC, but a lot of possibilities. So those are fairly ductile metals. And then if we look at HCP quickly, hexagonal close packed, let's just draw our sort of expanded unit cell that we had back in chapter 3. Remember, these are made up of close packed planes of atoms that are stacked on top of each other. I'll shade those planes in. There's one. There was one triangular one in the middle. One right here. And those we called the basal planes. They're the 100 type planes. Or actually 001 type planes. Let me redo that. 001 type planes. And in our 4-digit notation, that's 0001 type planes. And each of those planes, there's really only one set here. There's only really one type of plane, those basal planes that cut across there. And each of those planes has 3 different directions. So I'll draw those down here at the bottom. There's one there, one here, and one here. And if I take, we could take the atoms out and sort of look at this hexagonal array. Here are the directions we were just talking about. So what we could say here is there's only one type of plane and 3 directions. So we really only have 3 slip systems. So another thing we could say here is limited possibilities. And that's why the hexagonal close-packed metals are notoriously not as ductile or easy to form as BCC or FCC metals. So what are those metals? Just to remind you, those are titanium, magnesium, zinc, beryllium. There are lots of others. But titanium is a great metal, very strong, lightweight, but it's one of its limitations is it's not so easy to get into shapes like the other metals because there aren't very many possibilities for slip. Now here's a table from your book that describes the slip systems for different metals. And you can see here, we kind of touched on for FCC, there was these 111 type planes and the 110 directions, and there's 12 possible slip systems. For BCC, the primary ones with the highest density for most BCC metals is this first row, but you can see they've even listed some other possibilities for slip for some other BCC metals. And then for HCP, for most of those, really we've only got a few possibilities here. So like we said, limited possibilities. There are some other slip systems that can operate, but they're just not as easy because they're not as close packed as some of the others. So they aren't quite as important as, this first one that I'm circling here. But again, the idea is the possibilities for slip for hexagonal is limited compared to those other metals. That kind of leads to some interesting behavior here. Let's talk about observed behavior for a HCP metal. We've talked about this before. For, we'll say HCP single crystal. Let's say I have a single crystal of zinc or something like that, and I pull it in tension. Pull in tension. And so we've got a single crystal here. And let's say that the slip planes, there are only one set, we said. Let's say they're oriented like this. Well, the observed behavior is that things slip along those planes. And so we observe blocks of material kind of slip like this. Those are called slip steps or slip lines. So that's how the crystal deforms. And there's a figure from your book here that I'm going to show you that it talks about this. Here are the slip planes. They're oriented in a certain orientation. There is some component of this stress acting in shear, and then there's some kind of perpendicular. And so what we observe is what we see on the figure on the right, which is these slip steps in this single crystal. Now that kind of leads to some interesting behavior that we could talk about. And the idea is, what if we could orient the slip planes in a certain orientation relative to the stress? And we'll talk about that here in a little bit. So let's go on and let's talk about this concept of resolved shear stress. And I'm going to draw a figure first from your book. So the idea is, if we know the orientation of a single crystal, and we know that we have a tensile stress in a certain direction, and we're interested in what is the shear stress on a certain plane. So here's our plane that I've drawn, in a certain direction on that plane. So here's our resolved shear stress. And we're going to call this direction right here the normal to that plane. That we can figure out what the resolved shear stress is, that is tau sub r, on that plane in this certain direction here, if we know these angles, phi and lambda, and I'm going to define those angles here in a second. So we're going to write an equation and we're going to talk about it. The resolved shear stress, tau sub r, is the tensile stress times the cosine phi times the cosine of lambda. Now I have those angles pictured over there, but let's define them. So phi is the angle, that's my symbol for angle, it's the angle between the applied stress, that was sigma, applied stress, and the slip plane normal. Normal. That's the normal direction to the slip plane. Perpendicular direction to the slip plane. And lambda is the angle between the applied stress and the slip direction. Or we could call that the shear direction. So if we know those angles, we can calculate how much of the component of stress is operating here in this. Here, let me use, got the laser pointer here, see if this works. How much is in this direction on that plane? And remember, it's a shear stress that causes slip. Now looking at this, here's the figure that we're talking about. So if I know the slip direction and I know the normal to the slip plane, we can calculate what the resolved shear stress is on that plane in that direction here. So that's kind of the figure that I had before. Now, let me draw a picture next to this. Another thing that we could talk about is, let's say that we knew this was an FCC, or let's say it's an HCP material, and we have a stress in a certain direction, one of the things we're going to talk about in a bit is, well, which slip system is going to be preferred for slip. Let's say that this slip plane right here that I've drawn is oriented like this, and I have 3 directions on that slip plane. 1, 2, 3. If I asked you all which one of those slips easiest, or which one of those directions is there the greater component of this tensile stress, if you look at it, it kind of looks like there's more of a component here in this one direction than those other two. More of the component of this tensile stress acts in that direction than those other 2 directions. So if we talked about which slip system would be preferred in this situation, you'd probably say it would be 1, because it looks like it's the most favorably oriented relative to that external stress. So we'd say this looks easiest on that one. So that's going to be related to something we're going to talk about here soon. Or you could say most favorable for slip on that direction, on that plane. Okay, so let's define another term that's related to this. So let's define this term critical resolved shear stress. So we've talked about resolved shear stress. Now we've got this term critical resolved shear stress. Now that's a little bit different. So this is called tau sub CRSS, critical resolved shear stress. And this is defined as, so the definition is a material property it's the minimum shear stress needed to initiate slip in a certain, or we'll say on a certain plane, or on a, here let's cross that out, let's say on a slip plane in a certain direction on that plane. Another way that we could put this is we could say if the resolved shear stress, tau sub r, is greater than or equal to the critical resolved shear stress, which is a material property, then we can say slip occurs. That is, if the resolved shear stress builds up to a big enough value where it exceeds the critical resolved shear stress, then it can slip. So in other words, when I was pushing those ping pong balls around, I was applying a shear stress, but I had to apply a certain amount of shear stress in order for it to kind of slip. It doesn't just happen at any shear stress, it's got to build up to a critical value. Now we could talk about a few different cases here of orientation, but what if I had the stress oriented like this and the slip planes were oriented horizontally? Well, you can see that the resolved shear stress here is going to be 0, because, to go back to our equation from the last, the angle between the slip direction on that plane and the tensile stress is 90 degrees, so the cosine of 90 is 0. So in other words, there's no component of shear stress on that plane. You can see it's perpendicular, in other words, right? We could take a look at a situation like this. It's at a max here. Tau sub r max is equal to sigma over 2. That's when phi is 45 degrees and lambda is 45 degrees. And those of you that have had some mechanics and statics know that the maximum shear planes are at 45 degrees relative to a tensile axis. And finally, we could say, well, what if the slip planes were oriented vertically, like this? Well, in this case, the resolved shear stress is 0 again, because now phi is 90 degrees. Now that kind of thing leads to some interesting behavior that we could even take advantage of. So let's just say that, so we'll call this interesting behavior. We'll say HCP metal turbine blade. So let me draw sort of a schematic of a turbine jet engine. So we've got these blades here that are oriented like this, right? And here's our turbine. I haven't drawn all the blades, but let's say we blow up what's going on in this blade right here. What if we could orient, so let's say it like this. What if we orient, or intentionally orient like this, where the slip planes are perpendicular to the tensile stress? Well, if we do that, you can't have slip, so we'll say no slip, right? Because those planes are perpendicular to the tensile stress here. And that we could take advantage of that, and so we could say now it takes a very large stress to deform and break these blades, because we've oriented those single crystals such that there's no component of shear stress on those planes, so slip can't occur. So we can take advantage of this in certain circumstances. Now we're going to do an example problem here, and it's kind of involved, and I'm going to work it a couple of ways. And I'm glad I'm recording this so you can go back and review this, because they aren't the easiest problems. But what we're going to do is we're going to do a resolved shear stress example problem. So here's our example. If a stress, we'll just say sigma stress, of 20 MPa is applied to an FCC single crystal in the 0, 0, 1 direction. That's the z direction, by the way. What is the resolved shear stress? That's tau sub r, resolved shear stress. On the 1, 1, 1 plane in the 0, 1 bar 1 direction. Okay, let's kind of draw a picture of what we've got going on. So I'm going to kind of draw this from a unit cell perspective. There's an example problem in your book that's like this. But let's draw a unit cell representation. And we've got the stress going in the z direction. So I'll put the stresses in this direction, z direction. Here's x and y. And we're interested in the 1, 1, 1 plane, so I'm going to draw that here. So here's our 1, 1, 1 plane. That's the slip plane. And we want the O 1 bar 1 direction. And remember, there's 3 directions on that plane. I'm going to draw this in dark. This right here, the direction that I've drawn in really dark right there, that is specifically the O 1 bar 1 direction. So let's take a look at those angles that we talked about before. So first of all, we need the normal to the slip plane. That's this direction here. It turns out that the normal direction, so we'll call this N, normal, that is the 1, 1, 1 direction. Remember, the 1, 1, 1 direction is perpendicular to the 1, 1, 1 plane. The same named direction is perpendicular to that plane. So that direction's perpendicular there. So if we start looking at these angles here, let's first take a look at lambda. In this case, this is the easier one to visualize. So I'm going to change colors here with the pen so you can kind of see this. But phi is the angle right here. That's the angle between the stress direction, which is the z direction, and the slip plane normal. And then lambda is this angle, we could write it up here. It's the angle right here, lambda. It's the angle between the stress direction and this slip direction. And if you take a look at that, I'm going to draw it down here in the right corner or down here. Here's the z direction. That's lambda right there. Does everyone see that's 45-degree angle? It's a 45-degree angle. So lambda there is 45 degrees. We can tell just by looking at it. But phi is not so obvious. Phi is not so obvious. So let's take a look at that. The way we get phi is with this triangle that I'm going to shade in red here. So I'm going to use the laser pointer. It's this triangle right here. And phi is shown down below, but if we can calculate sum of those angles. So I'm going to take that triangle out, and here's phi down here. This distance is 1, this distance is the square root of 2, and this distance is the square root of 3. If you go through here, then phi is the angle whose cosine is 1 over the square root of 3, or you could say arc cosine 1 over the square root of 3. If you figure that out, phi is 54.7 degrees. And plug that in your calculator. So going back to our resolved shear stress equation, and now let's plug in what we know. So sigma is 20 MPa, and then phi is 54, so we have the cosine of 54.7 degrees times the cosine of 45 degrees. Or if you look at those triangles up above, the cosine of 54.7 is 1 over the square root of 3. And the cosine of 45, you guys already probably have that memorized from trig. It's 1 over the square root of 2. If you figure that out, the resolved shear stress on that plane in that direction is 8.2 MPa. So of that 20 MPa, 8.2 is acting in shear on that certain plane in that certain direction. Okay. Now, that drawing's getting a little hectic, and I'm going to show you an easier way to work these problems here in a second. But I do have a couple of follow-up questions on this one, on this example. So here are our follow-up questions to this. First one, what if the critical resolved shear stress for this material was equal to 10 MPa? Would slip occur? Well, the answer is no, because in that case, the resolved shear stress that we calculated was 8.2, which is less than the critical resolved shear stress. Remember, we said when the resolved shear stress was greater than or equal to the critical resolved shear stress, then slip could occur. Now, let's look at that situation that we had a second ago. I'm going to redraw that figure. Remember, we had this plane. Here's the 1, 1, 1 plane. And we looked at direction 1 on that plane. And remember, the tensile stress is in the z direction, so I'm kind of drawing that with arrows here. Well, what about the other two directions on that plane? I'll draw them in here. Here's direction 2, label it. So there's direction 2. And then here's direction 3 down here. Well, for direction 2, if you take a look at this, this has the same angle between the stress direction, the sigma or the z direction, as direction 1 had. So this is going to have the same, so direction 2 we'll say would have the same resolved shear stress. Tau sub r is 8.2 MPa. Let's look at direction 3. Well, what would the resolved shear stress be in direction 3? Well, if you take a look at that, do you all see that the stress direction, that's the z direction, where I've got the stress pointed, is perpendicular to direction 3? So there would be no component of resolved shear stress acting on that one. So we would say tau sub r is 0. Now we could do one last follow-up question, which is to say, which of these 3 directions would be preferred for slip? Well, you would say 1 and 2 are equally preferred, and 3, slip cannot occur at all. All right? So that's the idea of when we talk about, preferred orientation. So let's go on and let's talk about the relationship of the critical resolved shear stress to the yield stress of the material. So before, we had this situation where we knew what sigma was, and we wanted to figure out, well, would it slip on a certain plane, and what would tau be? Would it be enough to slip? That was working the problem this way. That was figuring out the resolved shear stress. That's this equation that we had. Well, we could kind of work the problem backwards and say, well, if we knew what the critical resolved shear stress would be to make it slip, what would the stress up here have to be to make it slip? That would actually be the yield stress, if you think about it. So we could rearrange this equation and just solve for the stress. And we could say the yield stress is the critical resolved shear stress over cosine phi cosine lambda. So that's kind of like working the problem backwards. And remember, we'll put an arrow in here if tau sub r is greater than the critical resolved shear stress, then slip occurs. So if we know what the critical resolved shear stress is for the material, we could calculate what would the external stress have to be in a certain orientation to make it slip. It's kind of like, working the problem backwards, like I said. Now, we're going to do one last thing before we quit on this lecture, and that is we're going to work this problem that I just did as an example using an easier method where we don't have to draw it out and we can use the dot product. So let's take a look at that. Let's do an example. This is similar to example, so easy way to work these resolved shear stress problems. And I'm going to put the easy way is to use the dot product, which you've all done before, but we're going to remind you how it works. And so let's restate our equation here. So we had 20, and again, this is similar to example. And let's put it like this. Let me erase that. Similar to example 7.1 in your book. Okay, but again, to remind you what the problem we just worked is, remember we had 20 MPa in the 001, that's the z direction, and we wanted to calculate the tau sub r, or resolved shear stress on the 1, 1, 1 plane in the O1 bar 1 direction. So we're going to work that same problem that I just drew out, and we kind of worked with some trigonometry, geometry, but this time we're going to do it with the dot product in a much easier fashion, okay? So remember, we had this equation for the resolved shear stress was the stress times the cosine of phi times the cosine of lambda, where the cosine of phi was the angle between the slip plane normal and the stress direction, and lambda was the angle between the stress direction and the slip direction. We defined those before. But let's go review the dot product here, okay? So let's do a review of the dot product. So to do, you can see in this equation up here above, we need the cosine of the angles. Well, if you go back and look at the definition of a dot product between two vectors, it gives you the angle between two vectors, that it's involved in that calculation. So the review of the dot product, so if I have vector A dotted with vector B, you can see they're not the same length there, and the angle between those is theta, the definition of the dot product is this: vector A dotted with vector B is equal to the magnitude of vector A times the magnitude of vector B times the cosine of the angle in between. Well, that cosine is what we're going to take advantage of here in this calculation. Now, I hope that you all remember how to calculate the dot product between two vectors, but let me just remind you, let's just say, I'm going to go over here to the left. Let's say that I have 1i plus 1j plus 1k, and I want to dot it with vector 0i plus 1j plus 1k. Remember how to do that? You take the first number times the first plus the second times the second plus the third times the third. So in this case, you get 1 times 0 plus 1 times 1 plus 1 times 1, so you get 2. You guys all remember that. And then how do we calculate the magnitude of a vector? So how do you get the magnitude of 1i plus 1j plus 1k? Well, you all remember it's the square root. So the magnitude is the square root of the sum of the squares. So for that vector that I just had over there, 1i plus 1j plus 1k, the square root of the sum of the squares is the square root of 1 squared plus 1 squared plus 1 squared, so it's the square root of 3. So we're going to use this definition of the dot product here to calculate those angles that we want. So we don't need to even draw the thing out. If we know these directions, we can calculate the angles really easily. So let's do that. So I'm going to go on to the next slide here. So remember, the angle phi was the angle between the the stress direction. So that was 0, 1. So I'll put above it, that's the stress direction. And the slip plane normal, which we remember was the 1, 1, 1 direction because that's perpendicular to the 1, 1, 1 plane. So to use this dot product, what do you get when you take the dot product between those two direction vectors. Well, if it's the first times the first plus the second times the second plus the third times the third, you just get 1, because it's 0 times 1 plus 0 times 1 plus 1 times 1. So you get 1, so that's the dot product. And that, remember, that equals the magnitude of vector A. So that's the magnitude of the first one. Well, that's the square root of the sum of the squares for that first vector, which is 001. So that's just the square root of 1. And then the magnitude of the second vector, which is the square root of 1 squared plus 1 squared plus 1 squared, so that's square root of 3, times the cosine of the angle in between, which is phi. So the cosine of phi is 1 over the square root of 3. Similarly, lambda is the angle between the stress direction and the slip direction, which was, if we go back to the last page, it was the O1 bar 1 direction. O1 bar 1 direction. Well, let's do that same calculation. So what do you get when you take the dot product? Well, it's 0 times 0 plus 0 times negative 1 plus 1 times 1. So we get 1 again, and that's equal to the magnitude of vector A, which is the square root of 1, times the magnitude of the second vector, which is the square root of the sum of the squares again. So that's square root of 2 cosine lambda. So cosine lambda is 1 over the square root of 2. So if we go back to our equation, the resolved shear stress is 20 MPa times this cosine of lambda, which is 1 over the square root of 3. We don't even need the angles. We want the cosine anyway. Times 1 over the square root of 2. That's 8.2 MPa. So we just used the dot products to figure out what those angles were that we needed instead of drawing them like we did back here. So I'm going to go back, but you'll see the same 1 over square root of 3 and 1 over square root of 2 because those are the cosines of those two angles from before. So back here on this slide, use our laser pointer, right? Those were those two angles, but we didn't even need the angles. We needed the cosine anyway. And see, they're the same as what we drew out before. But now we don't have to draw out that complicated drawing over here. We can just use the dot product to figure those out. So let's go back to where we were. Now, again, let me draw here one last thing, and that is refer to example 7.1 in your book, because example 7.1 in your book has this big long equation for calculating angles. But what you can see if you just look at that big long equation, I'm not even sure they tell you where they get it. It's from the dot product, because what you see on top is first times first plus second times second, and what you see on bottom is the square root of the sum of the squares. So remember, we can just use the dot product to make this calculation really easy. All right, that's not an easy problem, but I'm glad we wrote it down because you can kind of follow it along. And now if we know the stress in any direction and we know what, slip system we're interested in, we can figure out what the resolved shear stress is, and we can figure out would it slip or which slip system is most favorably oriented for slip. All right, that's the end of this lecture.